Do you believe this hat exists? I know. Can you believe that in the 80s they had songs about turning Japanese? I don't know. Crazy. Thanksgiving's a crazy time. It's also a great time to talk about electrical potential and energy. And that's what we're going to do today. So let's get going. Okay, electric potential is basically our thing that we use to figure out energy. We can also use it to find electric field. They're all kind of interrelated, but it's the thing that tells us how much electrons want to move from one place to the other. And it's kind of a hard thing to conceive of. So we gotta use some tricks, sort of. It's what we use to find the electrical energy too, and it's called V for voltage, and it's measured in volts. And we want to call it voltage, but we want to try to keep ourselves from doing that and call electric potential because that helps us keep straight what it is. And since it's such a hard concept anyway, we want to try to do that. Feel free to correct me if I call it voltage because it's not. It's electric potential. And the same way we used height when we were talking about gravitational force and energy, like mgh. Potential is similar to that for electricity. It's what we use to calculate the energy. And so a lot of times we even draw pictures where we use height to represent different potentials. If we go from 0 volts to 5 volts, we have to go up, and so we have to give it some energy somehow. And if we're going from 5 down to 0, we can get some energy back out, the same way we did for gravitational heights. So a lot of times we think of V as the H of electricity. Wow, I thought it just didn't work there. You get it. Tricity. Closer. Anyway, notice that when we have two lines of charge in this picture right here, we have an equation for the potential that is just the electric field times the distance between them, and that's a constant constant electric field between those, and the voltage is the difference between the two plates. But really the one we use the most often is this V equals kq over r. kq over r, and that's the potential from any given point charge. So this picture down here has a point there, and then we have different amounts of potential at different distances away from it, and we can figure out how much that potential is by putting it into this equation here. And just to remind you, the electric field and the force equations are very similar. Notice they all have K's and Q's and R's, so we have to try to remember in our head how they're different, and V as an R instead of an R squared like the electric field and the force ones do. So that helps us keep them apart. And again, the AP uses 1 over 4 pi epsilon naught, but we're probably going to use K, and K being 9 times 10 to the 9th. One of the nice things about potential is that it is a scalar. Being a scalar means that we don't have to worry about the sines and cosines like we were having some problems with on force and electric field. If we have a positive charge and we have a negative charge, we want to find the potential at some point, we can find the potential from the positive charge with this R and that charge, and then find the potential from the negative one here with that R and that charge, and then just add the numbers, one being positive, one being negative. Makes life a lot easier for that part of it anyway. Notice that potential is constant inside of a conductor because we already said electric field is constant inside of a conductor, and we know that if there's no change in electric field, V equals ED, that means that there's going to be no change in my potential. Potential is caused by a change in electric field, so if electric field is always 0, we have a constant potential. If you remember with our electric field lines always were away from positives and towards negatives. So if we drew a bunch of electric field lines on these two charges, they go towards the negatives, away from the positives. Now my V lines, constant potential lines, are always 90 degrees to those electric field lines that I just drew. So if I take a different color and say, okay, I'm going to go 90 degrees to each one of these lines around there, in between those, because I'm the same distance away from the charge, I get a circular constant potential. And I get a circular constant potential on a positive too. Notice wherever I cross, they're at 90 degrees. Little 90 there. The difference in that is that this one's going to have a negative potential, that's going to be a positive potential. And sometimes that's hard to see in 2D. So what we can do is we can say this is a plus and this is a minus, and we can make a little graph of potential versus position. And if we say as we go across this, my position is going to get bigger. When I'm really close to that plus, I'm going to have a very, very positive potential. And since that is a conductor, it's got to be constant there. This one's going to have a negative potential. It's going to be constant there. As I come up to that, I fall off as v squared and v squared and v squared. And if you notice, this is like that height thing that we said, that v is the height of electricity. If we think of potential as going uphill towards a positive, downhill towards a negative, and so if we wanted to see which way a positive would go, it's always going to go downhill. See? Nice. And these constant potential lines are what would happen if we took and we sliced there and there. We get a circle around this one and a circle around that one. That's how we get those exact potential lines. It's like a topographical map for potential. You know, topographical maps tell you a constant height. This is telling you constant potential lines. So it's a weird concept, but it's not really that difficult. Notice those are all potentials, and remember, along a constant potential there's no work done because there's no change in energy. Okay. Because we talk a lot about the inside of conductors, we end up having to do some problems. The AP likes to do problems on what's called nested spheres of charge. And so what they'll do is they'll put a circular ball here and another one inside that ball, and they ask us things about what the electric field and the voltage is at different places, like inside both of them, inside just one of them, or outside both of them. And they'll put different charges on each one over here, so we have to know what happens inside of them. And remember that basically inside both of them, the E field is 0. And so if we get on this inside area, there's no electric field. If we get outside the first one, we're in this area here, the electric field from the outside one will be 0, but the inside one is going to be the equation. KQ over R squared, and so we have to figure out what it's going to be, how far away we are from this one, but not from this one in here, but not from that one out there, because that one's a 0. If we get outside both of them, electric field is going to be KQ over R squared for this one, and KQ over R squared for this one. As it moves away, it gets smaller for both of them. And for the voltage, it's constant if you're inside of it, and so if you're inside both of them, it's constant. If we're outside of this one, it's constant from the blue one, but not from the red one. So it gets kind of complicated, so we're going to draw you a better picture the next time. So here's our better picture. These blue things here represent the two nested spheres, and so we're in both of them. I said already that my electric field was 0 for both of them. The voltage is constant for both of them. See, I have a KQ1 over R1, Q1 being my charge for the first thing, Q2 being the charge for the second one. A Q1 over R1 because I'm constant and I'm inside of it, and the distance that I use for the constant thing is the radius of the whole sphere. And since I'm inside of this one also, I use this constant charge and this constant radius here, so I get a constant value, all the stuff in here. Once I get outside of the first one right here, I get an electric field from the interior one, and I do KQ1 over R, R being the radius where I'm at, so it can change as I go in between those two, but I get a 0 from the outside one. The voltage gets a little more complicated. My voltage is constant from the outside one because I'm inside of it, but in the inside one it's no longer constant. It uses the little radius where I actually am to calculate it, so that changes as I move in between the two. And when I get outside both of them, my electric field and my voltage are both changing with the radius, and I have to calculate each of them based on my position. Inside, constant voltage, no electric field. As I get outside of each one, I have to start calculating the changing electric field, and constant V inside and change as I get outside each one. So those problems can be a little confusing, but like if you look at the back of this picture and maybe look back at the one without any marks on it especially, and try to think through that and ask any questions you have, we'll get through it. Another way to visualize this is with a little graph, and so we did a graph of one sphere. So if we have one sphere up here that we're getting outside of, as our R gets bigger, this is our R, if we're inside of the sphere, it's a constant value based on the R that's on the outside, and it's a constant V and it's a 0 E. And right as we get to the R, this one jumps up to a pretty big value because remember our R is on the bottom, so when we're close it's a big value, and as I go away it goes off as R squared. My V up here was at a constant value and now it starts dropping off as an R, so it's not quite as steep as the bottom one right there. Both of them fall off as R goes, but one goes as R and one goes as R squared. They're both K, Q, so the top part's the same, the bottom part just makes this one steeper than that one. And the electric field is 0 and the voltage is constant inside the sphere. Today's Japanese snack is, you got it, sushi. Our new HEB has a pretty good sushi section. Look at this. Nice. Got some sashimi over here. That's not in a roll. Then I got some tuna, and I got me some salmon also. Gotta have your chopsticks. Man, I'm really hungry. Sushi. Pretty darn good. Sashimi. I'm pretty happy with that new HEB. I don't know about you. I got some good stuff there. So potential energy. Electric potential is just like every other kind. We can set it equal to other kinds of electric energy. Other forms of energy, so kinetic energy or other potentials. And notice that it's V that we use to find it. We take our voltage times whatever charge we're going to put there. So just like electric field was a quick way to find the force, voltage is a quick way to find the energy. And that's why it's similar to height, because height was a quick way for us to find gravitational potential. And this picture right here is one of the biggest examples that they use for this kind of energy. They'll say we have a capacitor, which is just basically two plates, one of which has negatives, one of which has positives. We put an electron right here. We know that electron's going to want to leave and go away from the other electrons. And we want to know how fast it's going to be if we put one little hole over on this side, so it's attracted by those, it's going to be going through. We want to know how fast it's going. We can set the electrical energy, QV, equal to 1/2 mv squared. We have to know the mass of an electron, and we can find the speed that it leaves the capacitor at. That's AP's favorite one with electric potential. We can set it equal to any kind of energy, really. And then we do different kinds of problems later on to do that. This right here is just telling us that this is very similar to our work formula, because if we take the force, the electrical force, K, Q1, Q2 over D squared, and multiply by the distance that is moving, which is just the D, we get our equation for electric potential energy, which is K, Q1, Q2 over R. Yeah, and these K's and Q's and R's are getting a little confusing. So we make a little chart to help us out with that. And we make a little four square thing. Notice this says scalar here. This one's vector. We have one charge and two charges, so we can keep them straight in our head. And we know that the two vectors are force and electric field. And both of those have R squareds in them. So R squareds go with vectors. Potential and energy are both scalars. And those only have an R in them instead of an R squared. Potential and electric field are the ones that we use to calculate the other one, and those only have Q in them, not Q1, Q2, because we're setting it up and we want to be able to put a charge in there and figure it out really quickly for a lot of different things. And the things that have two charges are the ones that we actually use mostly in problems where we're actually going to other types of energy other than electrical energies and forces. Notice that as we move this way on our graph, we have multiply by Q each time. So we're going potential to energy, we have multiply by Q. We're going from a field to force, we multiply by Q. Obviously, when we go backwards, we divide by Q. I want to put dots. And when we're going from scalar to vector, we divide by R. Notice it's R squared and R, so we take it and we divide by R. If we're going back the other way, we would multiply by R. But they're all really interrelated, so it's good to have this in your head to keep them straight so you don't mess up and use the wrong formula at the wrong time. We already sort of described some capacitors, so let's go ahead and do some talking and some equationing about them. Capacitance is the ability of two plates to hold charge. It's always two plates, and so you always have some kind of charge. Always one's going to be positive, one's going to be negative, and you're going to have a voltage across them. Say this is V2 and V1. And so our basic equation for capacitance is how much charge something can hold for the voltage that you put across it. So these over here are pretty big capacitors. And this is what a small capacitor looks like, mostly in computers and small circuitry. But like these two right here, those are big ones. And You gotta watch out if you ever see one of those in something, because you can really hurt yourself with that. So if we know the capacitance, we can find how much charge it will hold, but finding that capacitance is what this equation is for. And there are a lot of factors that go into that. One is a constant having to do with the substance that you're in. The second is a constant that has to do with the universe that we're in, that E sub aught one. But the main thing about it is the area that overlaps in my two capacitors. I said it was two plates, and I kind of tried to make it 3D in this picture so you can see the two different plates, and then the distance apart they are. The closer you get together, the more charge they can hold, because the more they attract each other, and the more area you have, obviously the more charge it is. So if you have two plates, and I'm showing to you from a side view, it's only this bit area that I care about, not the other parts over there. And so that's how all the variable switches that you see work. What you have is you have two half circles, one of which is attached to a knob, and then when you twist your knob, this one moves up there so that the area that it covers up gets bigger and bigger and bigger, and so we get a higher and higher capacitance, and that allows us to have variable switches on our lights, which is very convenient. We have 3 energy equations for capacitors. Because really, that's what capacitors are for, is to store charge. And so we want to be able to put charge in them and then use them to do other things. And we take the first one, the U equals 1/2 QV, and we put the definition of a capacitor into one or the other of those two things to get the other two equations. But because we're doing energy so much with the capacitors, we want to be able to use whichever formula works for whichever situation we're in. And we can set these energies equal to any of the other ones. So we could say we have a capacitor that's fully charged with so much voltage and so much charge. 70% of that goes into making a motor run, because that's what electric cars are, is a big capacitor. Make it go. How fast is the car going to be going? So we can set the energies equal, just like any other energy we have. There was a request for all of our formulas we put into one place, just so you can see them all in one picture. And so here is all of your formulas. Notice that these versions here are the ones that AP uses, and then the ones that we use are in red over on the side. A couple of them you have to have more than one equation, because like for the electric field, sometimes you do it based on force, and sometimes with K's and Q's and R's. Same thing with energy. Sometimes you do it with Q and V, and sometimes you use the whole big thing with K, Q1, Q2 over R. For a capacitor, we have 3 different capacitor energy equations that we can sometimes set equal to other energies. Remember that for our midterm, we're going to have all of the formulas for the whole year. Make sure and look back at your overall course resources and get the formulas. Start working on those, because we're getting kind of close to that midterm. You want to be ready. Vapors, turning Japanese. A piece of my 80s childhood. Hopefully it'll take you into Thanksgiving, or if you're a B-Day person, take you out of Thanksgiving. Hopefully you got something out of the potential, the energy. We'll talk about it in class. Good luck on that quest.